Hello, everybody. Welcome to the third video of the visualization on the Obsertelligence channel. So today, we're going to continue on where we left off last time. If you guys remember, we left off with these violin plots and overlaying some of the plots on top of one another. I highly and strongly recommend that if you have not watched the first two videos on the visualization stuff that we've covered, please go back and review those prior to continuing with today's overview. So with that being said, we're going to cover a couple of things today. We're going to cover KDE plots, and we're going to also cover a Pearson correlation heat map. So let's get started. So let's go ahead and do a KDE plot. So we can do SNS dot KDE, kernel density estimate plot. And what we can pass in, if you do Shift Tab, it will open up this window again, like what we discussed last time, where you can pass in your X, Y, you can pass in a shade, you can pass in the data that you're interested in. So with that, let's go ahead and pass in a couple of things. Let's go ahead and pass in X is equal to DF, which is a data frame that we imported from lecture 1. And let's go ahead and pass in, I'm going to select, for example, injection rate. I'm just randomly picking these as we go. And then Y, let's pass in DF. Let's pass in EUR, for example, per 1,000 feet again. Here's EUR per 1,000 feet. And let's just run this, see how this looks like. If you run this, here's your KDE plot. As I said, you can always change the size of these plots by saying PLT dot figure and then passing in the fixed size. If you just hit tab, it will try to autocomplete fixed size. And let's just do a 10 by 8 just to start off. And here we go. Here's your KDE plot. You can see injection rate versus EUR per 1,000 feet. We can always pass in a something called shade to shade it, make it kind of look fancier. So we can say shade is equal to true. Okay, if you run this, now you can see it actually shaded. So you can see those higher areas much better now. And then also let's do a C map, a color map, C map. And let's pass in, for example, there are different colors that you can pass in. If you accidentally type in a wrong color, for example, if you just type in green, it would tell you that, it doesn't exist. So it gives you a list of options that you can select from. You can actually, try any of these options and to see which one you like the most and then choose that. But let's just go ahead and select, for example, reds, okay? If you run this, and here we go, you can see it. So you can change this, make it shaded and create this plot. So this is called a KDE plot, which stands for kernel density estimate. If you want to get more information on it, I don't want to go, out of the scope of this presentation, but please refer back to the book, and it has all kinds of information about how these plots are actually created mathematically. Now, the next plot, let's do a Pearson correlation coefficient plot. Now, what is a Pearson correlation coefficient? Now, if you remember from, I think, a Pearson correlation coefficient is simply the covariance of X and Y divided by a standard deviation of X times standard deviation of Y. That's what Pearson correlation coefficient is. The range of Pearson correlation coefficient ranges from -1 to 1. -1 means there is a 100% negative correlation, and +1 means 100% positive correlation. So with that being said, let's go ahead and try to create a heat map of all these features that I have in my data set, which were all of these features. My category is it's going to be a categorical feature, so that's not going to be included in the heat map, but EUR per 1,000 feet, while spacing, all these features will be plotted against one another, and in the middle is going to show you the actual Pearson correlation for each of those. So with that being said, let's get started. So let's say SNS dot, let's just say heat map. And let's go ahead and do df. And we're going to pass in the actual data frame that we have. And I'd like to do df.core, which basically provides you the correlation, for that. And the default correlation is Pearson correlation coefficient. How do I know this? If you just hit Shift Tab, you can see here df.core. The default method is called Pearson. You can expand on this. You can actually choose other methods as well. You can choose Kendall or Spearman correlation, which is also very highly used in the data science, world. So for now, let's just stick with the default. And just for the sake of this, I'm actually just gonna put this, copy and paste it, put it here so we know what we're actually looking at. And then let's also do a color map, CMap of. Let's do, I like the cool, warm type of coloring in this case. And annotation and note is another thing that I can pass in, which will show the numbers. If annotation is equal to false, you're not going to see the numbers. But I'm going to actually put the annotation in there is equal to true. And then let's just run this, see what this looks like. Here we go. I generated this heat map, but you can see it's small and all the numbers are not being shown properly. If I, for example, remove this portion here and run, and it's not going to run, or if I just do, so what I'd like to do is just to show you that, here we go, that you have to define what you want to put in your heat map. So what I want to do now, I want to add a size to this. Let's do plt.figure and pass in fixed size as we've done. And let's just pass in, let's just do, I'm going to pick 20, for example, by 8. Just randomly pick and see how this is like. Here we go. Much better now. Now you can see all the parameters. You can see all that. We can even increase that to 10, for example. Let's see what this looks like. Here we go. That's even better. So you can play around with these sizes. Well, what you see is basically you see the Pearson correlation coefficient between each of these features versus one another. So, for example, in this case, it's showing that there is a negative 0.37 Pearson correlation coefficient between stage spacing and EUR per 1,000 feet. Basically, this is saying that as stage spacing increases, your EUR per 1,000 feet goes down, just from a simple, like Pearson correlation coefficient calculation. Or for example, lateral length, as lateral length increases, the EUR, for example, goes up, which is pretty standard. Injection rate, as injection rate increases, EUR per 1,000 feet goes up in this, for example, in this synthetic data set that we have. And you got proppant loading. As proppant loading increases, your EUR per 1,000 feet goes, also goes up. And this is one way of finding parameters that are collinear. So collinearity is defined as parameters that have high Pearson correlation coefficient with respect to one another. And, you want to take those parameters out of your machine learning model. And the reason for that is because you don't want to confuse your model with similar parameters that provide the same information. So it's highly recommended that parameters that provide similar information to be taken out. For example, if you have, porosity and TOC and all these geologic parameters that are calculated from one another, it's recommended to just choose one that provides similar information as opposed to choosing 10 of them and confusing your model. So this is just a Pearson correlation coefficient heat map. Let's just make it a little fancier. Let's actually, if you do Shift Tab, you can see all the options that you can pass in here. Let's pass in, let's just do line width and line color. So let's just do line width, and let's just pick a width of, for example, 4 in this case. And let's just do a line color of, let's just say black. like the black so you can see better. Here we go. Here's line width, here's line color. You can see here he added these black lines and kind of made it a little fancier, but you can maybe change it to 2. 4 is maybe too much, you know. But you can customize it to your needs, and you can see here's your Pearson correlation coefficient heat map. So I can always call this Pearson correlation coefficient heat map. And feel free to, as I said, the equation is pretty simple, just covariance of x and y divided by standard deviation of x times standard deviation of y. So I can just actually highlight it as like this. Pearson correlation coefficient heat map. And then, you know, we can, if you want the other parameters, such as, let's do Spearman correlation coefficient, you can just pass in that. So you can see, you can pass in Kendall, Spearman. Spearman is another mathematically correlation coefficient equation that you can use. It takes into account the ranking, subtracting the ranking, squaring that. And then it also takes into account the number of samples to calculate the Spearman correlation coefficient. You can also use that. We've covered it extensively in the books. It's beyond the scope of this lecture here, but you can simply go here and change the Pearson to, I think it's, make sure it's the, it is the lowercase Spearman. Yeah, so let's do that. Let's just paste it here. And you can run this. See, the numbers are not going to be the same. So for example, stage spacing had a minus 0.37. Your Spearman has a minus 0.45. But overall, if you look at the two, they're comparable. They're not like going to be like completely off, but the numbers are going to be slightly different, you know, because these are two different mathematical correlation coefficient equations that we're using in this case to construct this heat map. So you can also do Kendall. You can just simply copy and paste this and do Kendall. I believe it's called Kendall. Here we go. And here we go. You got another one. So you simply, actually, I got to change these to, this is called Pearson. This is called Spearman. And this is called Kendall. You know, within a matter of a few seconds, we're able to generate these heat maps that look nice and fancy and kind of see what's going on in your data set. You know, like immediately you can tell that prop and loading has a high importance on your EUR per 1,000 feet. This is just simply just doing simple analysis here. And you know, stage spacing has a large negative relationship. And you can look at it across these 3 different plots through Pearson correlation, Spearman, and through Kendall. So this is it that I wanted to cover for this lecture. If you have any questions, let me know. But in the meantime, if you like these videos, I do this as a fun hobby. If you like these videos, like and share, and we'll see you guys in the next video. Thank you so much.